This is the last lecture in the series of lectures on linear algebra for data science, and as I mentioned in the last class, today I am going to talk to you about the connections between eigenvectors and the fundamental subspaces that we have described earlier. We saw in the last lecture that the eigenvalue eigenvector equation results in this equation having to be satisfied, which is a minus lambda I equals 0. In general, we also saw that this would turn out to be a polynomial of degree n in lambda, which basically means that even if this matrix A is real, because the solutions to a polynomial equation could be either real or complex, you could have eigenvalues that are complex. So, for a general matrix, you could have eigenvalues which are either real or complex. And notice that since we write the equation Ax equals lambda x, whenever this eigenvalues become complex, then the eigenvectors are also complex vectors. So, this is true in general. However, if the matrix is symmetric and symmetric matrices are of the form A equal to A transpose, then there are certain nice properties for these matrices which are very useful for us in data science. We also encounter symmetric matrices quite a bit in data science. For example, the covariance matrix turns out to be a symmetric matrix, and there are several other cases where we deal with symmetric matrices. So, these properties of symmetric matrices are very useful for us when we look at algorithms in data science. Now, the first property of symmetric matrices that is very useful to us is if the matrix is symmetric, then the eigenvalues are always real. So, irrespective of what that symmetric matrix is, this polynomial would always give real solutions for symmetric matrices. And as I mentioned before, if this turns out to be real, then the eigenvectors are also real. Now, there is another aspect of an eigenvalues and eigenvectors that is important. If I have a matrix A and I have n different eigenvalues lambda 1 to lambda n, all of them are distinct, then I will definitely have n linearly independent eigenvectors corresponding to them, which could be nu 1, nu 2 all the way up to nu n. However, if there are certain eigenvalues which are repeated. So, for example, if we take a case where eigenvalue lambda 1 is repeated, then I could have some polynomial which is like this. So, the polynomial, original polynomial has eigenvalue lambda 1 repeated twice, and then there is another n minus 2th order polynomial which will give you n minus 2 other solutions. Now, in this case, when I have lambda 1 repeated like this, then it could turn out that this eigenvalue either has two eigenvectors which are independent, or it might have just one eigenvector. So, finding n linearly independent eigenvectors is not always guaranteed for any general matrix, and we already know that eigenvectors could be complex for any general matrix. However, when we talk about symmetric matrices, we can say for sure that the eigenvalues would be real, the eigenvectors would be real. Further, we are always guaranteed that we will have n linearly independent eigenvectors for symmetric matrices. It does not matter how many times the eigenvalues get repeated. One classic example of a symmetric matrix where eigenvalues are repeated many times. So, take identity matrix, something like this here. This identity matrix has eigenvalue lambda equal to 1, which is repeated thrice, but it would have three independent eigenvectors 1 0 0, 0 1 0 and 0 0 1. So, this is a case where eigenvalue is repeated thrice, but there are three independent eigenvectors. So, this is also an important result that we should keep in mind. And as I mentioned in the last slide, symmetric matrices have a very important role in data sciences. In fact, symmetric matrices of the type A transpose A or AA transpose are often encountered in data science computations. And notice that both of these matrices are symmetric. So, for example, if I take A transpose, this will be A transpose, transpose, which will be A transpose A. So, the transpose of the matrix is the same. You can verify that AA transpose is also symmetric through the same idea. So, we know matrices of the form A transpose A or AA transpose are both symmetric, and they are often encountered when we do computations in data science. And we know from the previous slide I had mentioned that the eigenvalues of symmetric matrices are real. If the symmetric matrix also takes this form or this form, we can also say that while the eigenvalues are real, they are also non-negative. That is, they will be either 0 or positive, but none of the eigenvalues will be negative. So, this is another important idea that we will use when we do data science, when we look at covariance matrices and so on. Also, the fact that this A transpose A and AA transpose are symmetric matrices guarantees that there will be n linearly independent eigenvectors for matrices of this form also. Okay. So, what we are going to do right now is, because of the importance of symmetric matrices in data science computations, we are going to look at the connection between the eigenvectors and the column space and null space for a symmetric matrix. Some of these results translate to non-symmetric matrices also, but for symmetric matrices all of these are results that we can use. So, we go back to the eigenvalue eigenvector equation. A nu is lambda nu, and this result that we are going to talk about right now is true whether the matrix A is symmetric or not. If A nu equals lambda nu, we ask the question, what happens when lambda is 0, that is, one of the eigenvalues becomes 0. So, when one of the eigenvalues becomes 0, then we have this equation, which is A nu equals 0. So, we can interpret nu as an eigenvector corresponding to eigenvalue 0. We have also seen this equation before when we talked about different subspaces for matrices. We saw that null space vectors are of the form A beta is 0 from one of our initial lectures. You notice that this and this form are the same. So, that basically means that nu, which is an eigenvector corresponding to eigenvalue lambda equals 0, is a null space vector, because it is just of the form that we have here. So, we could say the eigenvectors corresponding to 0 eigenvalues are in the null space of the original matrix A. Conversely, if the eigenvalue corresponding to an eigenvector is not 0, then that eigenvector cannot be in the null space of A. So, these are important results that we need to know. So, this is how eigenvectors are connected to null space. If none of the eigenvalues are 0, that basically means that the matrix A is full rank, and that means that I can never solve A nu equal to 0 and get non-trivial nu. So, it is not possible if A is full rank. So, if A is full rank, I cannot solve for this and get non-trivial nu. So, whenever lambdas are such that there is no eigenvalue that is 0, that means A is full rank matrix. That means there is no eigenvector such that A nu is 0, which basically means that there are no vectors in the null space. Now, let us see the connection between eigenvectors and column space. In this case, I am going to show you the result, and this result is valid for symmetric matrices. Let us assume that I have a symmetric matrix A. And the symmetric matrix A, we know, will have n real eigenvalues. Let us assume that R of these eigenvalues are 0. So, this R could be 0 also, that means there is no eigenvalue which is 0. So, even then all of this discussion is valid, but as a general case let us assume that R eigenvalues are 0. So, there are R 0 eigenvalues, and since we are assuming this matrix is n by n, there will be n real eigenvalues of which R are 0. So, there will be n minus R non-zero eigenvalues. And from the previous slide we know that the R eigenvectors corresponding to this R 0 eigenvalues are all in the null space. Okay. So, since I have R 0 eigenvalues, I will have R eigenvectors corresponding to this. So, all of these R eigenvectors are in the null space, which basically means that the dimension of the null space is R, because there are R vectors in the null space. And from rank nullity theorem we know that rank plus nullity is equal to number of columns, in this case n. Since there are R eigenvectors in the null space, nullity is R. So, the rank of the matrix has to be equal to n minus R. So, that is what we are saying here, and further we know that column rank is equal to row rank, and since the rank of the matrix is n minus R, the column rank also has to be n minus R. This basically means that there are n minus R independent vectors in the columns of the matrix. So, one question that we might ask is the following: we could ask what could be a basis set for this column space, or what could be the n minus R independent vectors that we can use as the column subspace. So, there are a few things that we can notice based on what we have discussed till now. First, notice that the n minus R eigenvectors that we talked about in the last slide, the ones that are not eigenvectors corresponding to lambda equal to 0, they cannot be in the null space, because lambda is a number which is different from 0. So, these n minus R eigenvectors cannot be in the null space of the matrix A. So, let me write again, we are discussing all of this for symmetric matrices. We know that all of these n minus R eigenvectors are also independent, because we said irrespective of what the symmetric matrix is, we will always get n linearly independent eigenvectors. So, that means these n minus R eigenvectors are also independent. We also know that each of these independent eigenvectors are going to be linear combinations of columns of A. To see this, let us look at this equation. So, let me write this out. So, I could call this as A. I am going to expand this nu into nu 1, nu 2 all the way up to nu n. Notice that these are components of nu, we are just taking one eigenvector nu, and then these are the n components in that eigenvector. I can write this as lambda nu, and from the previous lecture of how to do this column multiplication and how to interpret this column multiplication, I said you could think of this as nu 1 times the first column of A plus nu 2 times the second column of A all the way up to nu n times nth column of A equal to lambda nu. Now, in this equation, let me be very clear, these are scalars which are components in the eigenvector nu. These are column vectors, this is the first column of A, second column of A, this is nth column of A. This is again a scalar lambda, which is the eigenvalue corresponding to nu. So, this could be true for any of the n minus R eigenvectors which are not in the null space of this matrix A. Now, take lambda to the other side. So, you will have this equation as nu is nu 1 by lambda A 1 and so on plus nu n by lambda A n. Again, nu 1 is a scalar, lambda is a scalar. So, these are all constants that we are using to multiply these columns. Now, you will clearly see that each of these eigenvectors n minus R eigenvectors are linear combinations of the columns of A. So, there are n minus r linearly independent eigenvectors like this, and each of this are combinations of columns of A, and we also know that the dimension of the column space is n minus r. In other words, if you take all of these columns A 1 to A n, these can be represented using just n minus r linearly independent vectors. Now, when we put all of these facts together, which is the n minus r eigenvectors are linearly independent, they are combinations of columns of A, and the number of independent columns of A can be only n minus r. So, this implies that the eigenvectors corresponding to the non-zero eigenvalues for a symmetric matrix form a basis for the column space. So, this is the important result that I wanted to show you with all of these ideas. Now, again these results we will see and use as we look at some of the data science algorithms later. So, let us take a simple example to understand how all of this works. Let us consider a matrix which is of this form here. It is a 3 by 3 matrix. First thing that I want you to notice that this is a symmetric matrix. So, if you do A transpose equals A, and we said symmetric matrices will always have real eigenvalues, and when you do the eigenvalue computation for this, the way you do the eigenvalue computation is you take determinant A minus lambda I equal to 0, then you are going to get a third order polynomial which you set it equal to 0, and then you calculate the 3 solutions to this polynomial, and these would turn out to be the solution 0, 1, 2. And you take each of these solutions and then substitute it back in and then solve for Ax equals lambda x. Then you would get the 3 eigenvectors corresponding to this, which are given by this, this and this. Notice from our discussion before, since this is an eigenvector corresponding to lambda equal to 0, so this is going to be in the null space of this matrix A, and these are the remaining 2. How do I get this 2, which is 3 minus 1 n, n by n. So, it is a 3 by 3 matrix, and nullity is 1 because there is only one eigenvector corresponding to lambda equal to 0. So, I get 2 other linearly independent vectors, and in the last slide when we were discussing the connections, we claimed that these 2 eigenvectors will be in the column space, or in other words what we are claiming is that these 3 columns can simply be written as a linear combination of these 2 columns. And we are also sure that when we do A times nu 1, this will go to 0. So, let us verify all of this in the next slide. So, let us first check A times nu 1. So, this is the A matrix. I have A times nu 1 here, and you can quite easily see that when you do this computation you will get this 0 0 0, which basically shows that this is the eigenvector corresponding to 0 eigenvalue. Interestingly, in our initial lectures we talked about null space, and then we said the null space vector identifies a relationship between variables. Now, since this eigenvector is in the null space, the eigenvector corresponding to 0 eigenvalue or eigenvectors corresponding to 0 eigenvalues identify the relationships between the variables, because these eigenvectors are in the null space of the matrix. So, it is an interesting connection that we can make. So, the eigenvectors corresponding to 0 eigenvalue can be used to identify relationships among variables. Now, let us do the last thing that we discussed. Let us now check if the other 2 eigenvectors shown below. So, this is for the other 2 eigenvalues span the column space. So, what I have done here is I have taken each one of these columns from matrix A. So, this is column 1. So, this is A1, this is A2 and this is A3. Column 1 is 6 times nu 2, column 2 is 8 times nu 2, and column 3 is 2 times nu 3. So, we can say that A1, A2 and A3 are linear combinations of nu 2 and nu 3. So, nu 2 and nu 3 form a basis for this column space of matrix A. So, to summarize, we have A x equal to lambda x, and we largely focused on symmetric matrices in this lecture. So, we saw that if we have symmetric matrices, they have real eigenvalues. We also saw that symmetric matrices have n linearly independent eigenvectors. We saw that the eigenvectors corresponding to 0 eigenvalues span the null space of the matrix A, and eigenvectors corresponding to non-zero eigenvalues span the column space of A for symmetric matrices that we described in this lecture. So, with this we have described most of the important fundamental ideas from linear algebra that we will use quite a bit in the material that follows. The linear algebra parts will be used in regression analysis, which you will see as part of this course, and many of these ideas are also useful in algorithms that do classification. For example, we talked about Halfspaces and so on, and the notion of eigenvalues and eigenvectors are used pretty much in almost every data science algorithm. Of particular note is one algorithm which is called the principal component analysis, where these ideas of connections between null space, column space and so on are used quite heavily. So, I hope that we have given you a reasonable understanding of some of the important concepts that you need to learn to understand some of the material that we are going to teach in this course. And as I mentioned before, linear algebra is a vast topic. There are several ideas. How do these ideas translate? Which ones of these are applicable or not applicable for non-symmetric matrices and so on. And from the previous lectures, how do we develop some of those concepts more can be found in many good linear algebra books. However, our aim here has been to really cull out the most important concepts that we are going to use again and again in this first course on data science for engineers. More advanced topics in linear algebra will be covered when we teach the next course on machine learning, where those concepts might be more useful in advanced machine learning techniques that we will teach. So, with this we close this series of lectures on linear algebra, and the next set of lectures would be on the use of statistics in data science. I thank you, and I hope to see you back after you go through the module on statistics, which will be taught by my colleague Professor Shankar Narasimhan. Thank you.